Where's Alice? Is my wife here? Ah, good. Thank you for coming, Alice. And thank you, John. It's always nice to have an introduction by you. You make such nice introductions. 100 years ago, there were no broadcast engineers conferences. There were no radio conferences of any kind. Good evening, Carl. Wonderful. Good to see you. I would have been disappointed if you hadn't been here. Carl Smith. In fact, 100 years ago, there was no radio, period. How long is 100 years? It's a century. My talk will take a micro-century. That's a little less than an hour. So, 100 years is roughly 1 million hours. 100 years ago, in 1882, there was Morse's telegraph, there was Edison's incandescent light, but no radio. A few years earlier, in 1873, James Clerk Maxwell, a physics professor at Cambridge University, England, had published a book providing the first unified theory of electricity and magnetism. In it, he suggested that light was electromagnetic in nature, and that electromagnetic waves of greater wavelength might be possible. However, most scientists were skeptical, and some even attacked his views. But a few years later, in 1886, a physics professor at Karlsruhe, Germany, began some experimental studies of dielectric materials, which led him to schemes for producing electrical oscillations of long wavelength compared to light. And in the following year, he constructed and tested the first radio transmitter and receiver. His demonstration vindicated Maxwell's theory, and things began to turn in his favor after Hertz's demonstration. Heinrich Hertz was the father of radio, but his system remained a laboratory curiosity until 1894, when a young Italian, Guglielmo Marconi, vacationing in the Alps, chanced upon a magazine article describing Hertz's experiments. Wondering if Hertz's spark system could be utilized to send messages across space, Marconi became obsessed with the idea. He cut short his vacation and rushed home to Bologna. And in some rooms on the upper floor of his parents' spacious home, he assembled apparatus to repeat Hertz's experiment. And succeeding in this, went on to make improvements by adding tuning coils and large antenna and ground systems so that at longer wavelengths he could send signals over large distances. In 1901, he demonstrated radio transmission across the Atlantic Ocean. Ship-to-shore communication systems followed. Prior to that time, a ship at sea was completely isolated. Disaster could strike without anyone on the shore or on other ships being aware that anything had happened. Marconi changed all that, and his name became synonymous with radio, or wireless, as it was then called. Radio transmitters used spark, and everything was in Morse code. After World War I came vacuum tubes, continuous waves, voice modulation, and the first broadcast stations, KDKA, WGY, WGN, WOR, WFAA, WBAP, KFI, KPO, and many, many others. Then came FM and television broadcasting, both developing rapidly after World War II. After Sputnik came satellites, particularly ones in the Clark or geostationary orbit, equivalent to having your TV antenna on an invisible tower 22,000 miles high. October 4 of this year is the 25th anniversary of Sputnik 1. I've heard rumors and speculation that the Russians are planning something big and spectacular, like putting up a 100-man space station. Correction, 100-person space station with rooms for visitors. It will be called the Comrade Hilton. For European visitors, it will have such amenities as borscht and vodka. For American visitors, it will have caviar-flavored jelly beans. So now we have AM, FM, ground-based TV, satellite TV, we have broadcasting, we have narrowcasting, we have cable at radio wavelengths and with optical fibers, cable at light wavelengths. We have a global network of communication and broadcasting systems with new developments on an almost daily basis. And it all has come from Heinrich Hertz's epic experiments in Karlsruhe 95 years ago. Let's take a look at what Hertz used. This is a diagram of his transmitter, spark transmitter, consisting of a battery, spark coil, spark gap, dipole antenna, end-loaded dipole antenna, receiver, a loop receiver. When this was transmitting, he could get sparks on the receiver, loop over here, so that this was a complete system. Working at a wavelength of 5 meters, Hertz constructed the first radio transmitter, the first dipole antenna, the first radio loop, which acted as his receiver. It was simple and impressive. And I have constructed for this talk a replica of the Hertz transmitter over here, making it as authentic as possible, even to the rubber bands that were used. Hertz held things together with rubber bands. I will talk more about this a little later. But I would like to say that this one is low power. It only puts out about, less than 100 milliwatts. I have here a small spark coil, Model T Ford spark coil. And Hertz used a Ruhmkorff coil, which was used for exciting gaseous ignition tubes. There was a lot of work going on gaseous ignition back in those days, and his was much more powerful than this one. But what he did was, with his thank you, John. With his loop receiver, he turned on the transmitter, and then with the loop, got a spark here. When he turned this horizontal, it cut out. That demonstrated that he had polarization, a polarized wave. Backing away, he could see that it decreased in strength. And he did many other experiments. He reflected the waves from large reflectors. He built a large dielectric prism and refracted the waves through. He showed that these waves that he was generating had all of the same properties of light, except that the wavelength was 1,000,000 times longer. Beautiful experiment. Hertz did a tremendous amount of theoretical work leading up to this. Just reams of mathematics in one of his books. So that he was well grounded in the theory, he knew what he was doing, and it was an absolutely epic experiment. Looking at that, you would say that now probably we wouldn't build a transmitter like this, but you're wrong. There are over 100 million Hertzian spark transmitters, identical in principle to this one in operation in the United States today. We usually call them ignition systems. And every gasoline engine has one. It has the battery, the interrupter, the spark coil, has the spark gap, and the resonant radiating system, instead of being a dipole, is a loop. The ignition harness makes a beautiful antenna system. This is the modern version of the Hertz transmitter. Before Hertz, there was no radio. After it, think of all that has resulted. Yet in 1887, who could have foreseen what these brass rods and brass balls and metal cans might lead to? A Senator Proxmire would probably have given Hertz's experiment a Golden Fleece Award as a complete waste of time and money. Fortunately, there was no Senator Proxmire involved at that time, or you guys would be out of a job now. This concludes phase one of my talk. It's the historical introduction. It has been suggested that I include a little theory, but to please avoid vector analysis, tensors, and second-order differential equations. So, as phase two of my talk, I want to discuss antennas in ways that may be familiar and also in ways that may not. In my book Antennas, published in 1950, still in print and going strong, I defined an antenna as a transition region between a guided wave and a space wave, or vice versa. You take a transmission line, open it up. It's a small fraction of wavelength spacing here, so the wave stays with it, is guided. You open it up, so this is a wavelength or more. Most of the wave is radiated. So over here you have a space wave. Here you have a guided wave along the transmission line. Here you have a wave radiating out into space. It's radiation. It consists of radio photons. So this system is a electron-photon transition device. And the region between the guided wave and the space wave, the transition region, is the antenna. Now, if you arrange things so that the dimension, the spacing between the wires, the ratio of that to the diameter of the conductors is a constant. As you spread them out, you see the characteristic impedance of the transmission line remains constant. And if you make this big enough so you get no reflection off the end, you've got a flat line very broadband beam antenna out this way, having an impedance, or actually a radiation resistance equal to the characteristic impedance or resistance of that transmission line. Now, how big a frequency range could a system like this cover? Well, a somewhat more practical, more compact version is shown here. I've taken the conductors and brought them around here this way to reduce diffraction off the end. And in this system, in this antenna, if the dimension D here is no greater than a quarter wavelength at the long wavelength end, and this is no greater than a tenth of a wavelength at the short wavelength end, then taking the ratio of those two wavelengths and assuming that D over S is, say, 250, this antenna would have a bandwidth, an impedance bandwidth of 100 to 1, a very broadband antenna. At the long wavelength end, this would be a quarter wavelength, and at the short wavelength end, this would be a tenth of a wavelength. Continuing our discussion of antennas in a very general way, let me show an antenna that's kind of schematic. Looks like a horn antenna. Okay, that's all right. The important thing is that on the left side here, wait a minute. Yeah, that's left. We have a circuit element, two terminals over here. The antenna looks like a circuit element. We're dealing with electrons on conductors. Over on this side, we have a space wave. We have radiation. We have photons. The important characteristic is an antenna pattern. The antenna is the transition region. It interfaces a circuit in space. Now, to describe that antenna pattern can be rather tedious. It can require a lot of information. Here's a antenna pattern, main lobe, side lobes, back lobe, with a coordinate system. And in order to specify this pattern completely, we need to specify two components of the electric field, one in the theta direction, one in the phi direction, as a function of theta, phi, and distance. We also need to specify the phase difference between those two fields. So for all positions over a sphere. And if we take the total field, the squares of the total field, divided by its maximum value, integrated over a sphere, or 4 pi sterradians, we get what's called a beam solid angle, which is a scalar quantity that's very useful in describing the antenna pattern. There's a simpler way to get an approximation to this, that if you have a typical antenna pattern, you can take a cut through the theta plane and one through the phi plane and get two half-power beam widths, take their product. That's very nearly equal to this beam solid angle, omega sub A. It's an approximation, but surprisingly is usually better, much better than 1 dB from the exact value that you might get after a week's calculating with a big computer. Here is that relation. Now, if we divide that beam solid angle into 4 pi, we get what's called the directivity. And if your antenna is lossless, we call that the gain. If you don't want to work in sterradians, you can convert that to square degrees, 41,253 square degrees in a sphere. And then you can express your half-power beam angles in degrees. For example, you have a directional antenna symmetrical pattern with a half-power beam width of 10 degrees in the two principal planes. That gives you 100 in the denominator, a gain of 413 or 26 dB. If you have a broadcasting antenna, omnidirectional, 360 degrees in one plane and 8 degrees, say, in the vertical, you get 14.3 as the gain, or 12 degrees. It's a very versatile, useful relation. Going back now to the radiation patterns in a more complete discussion. The radiation patterns are three-dimensional. We have to have a lot of information. But as you saw, we can get a very simple quantity, a scalar quantity, which is extremely useful. It tells us a lot about the antenna. From this, we can get the directivity and the gain. And there is another quantity that we will talk about in a moment, the effective aperture of the antenna. These are all related to the field side of the antenna. On the circuit side, the input side, if you're transmitting, we have an impedance. The important part of that is the radiation resistance, because you can usually tune out the reactance. And you also have a temperature. Very important is the temperature of that radiation resistance. So those are the input quantities, T and R and T. Now, I'd like to demonstrate to you that the radiation resistance of an antenna depends on the antenna pattern. It's a function of the antenna pattern. The input part of the antenna is simply I squared R, where R is the radiation resistance at the terminals and I is the terminal current. That's the power radiated. If there's conservation of power, we're not losing anywhere, then out somewhere on a big sphere or big surface, if we integrate over that closed surface, we should also calculate the same power. This is the Poynting vector, and that's given by the field squared over the impedance of space. And we can rewrite it in terms of the maximum value, where this expression here is that pattern, beam solid angle omega sub A. And if I make an assumption about the maximum field being proportional to the antenna current and inversely proportional to the distance, some constant, we get this relation in the box, that the radiation resistance of the antenna is proportional to the beam solid angle. There's the impedance of space, and this is a constant. Z is 377 ohms, the impedance of space. If I make some assumptions about K and the fact that this antenna is isotropic, that is non-directional, the radiation resistance comes out as 120 ohms. So keep in mind that radiation resistance depends on the pattern. They're related. The antenna is the coupling device. Now, here is this directivity expression again. But I want to talk about these beam angles in a little different way. These two angles, the half-power beam widths, are also approximately resolution angles. If you have two objects in space and your half-power beam width is less than the angular separation, you can separate them. But if your half-power beam width is more than that, you cannot. So these are approximately resolution angles, and therefore the beam solid angle is a solid resolution angle. And dividing that into 4 pi, we get a number n, which is the number of sources that the antenna can resolve in the sky. So the directivity of an antenna is equal, or the gain if it's lossless, the gain of an antenna is equal to the number of sources the antenna can resolve. So say the antenna has 20 dB gain, that means that the antenna has can resolve 100 sources in the sky. We generally think of gain as meaning that if we put 1 watt in this antenna in the beam direction, we get the same power with our 1 watt as we would with 100 watts in a non-directional antenna. But for radio telescopes, we consider the resolution as being a very important quantity. The Ohio State University radio telescope at Delaware has about 60 dB gain, which means that it can resolve 1 million sources in the sky. And we have done sky mapping and have observed and mapped tens of thousands of radio sources, well below the theoretical limit that we could actually resolve. The quantity that I mentioned earlier, the effective aperture, is best considered if you're thinking about the antenna as a receiving device. Here we have a horn, an incident power per unit area, S is watts per square meter. The horn collects it, feeds it into a receiver, and the power available to the receiver, if everything's matched up and lossless, is equal simply to the power per unit area times an aperture, A sub E. Or this aperture is equal to the received power over the incident power density. For any antenna, regardless of what it is, there is always a uniquely defined effective aperture in square meters. And this comes into this expression. We can define the directivity in terms of the effective aperture over the square of the wavelength times 4 pi, and putting this relation and the other one for D involving the beam solid angle together, we get this very useful relation that the product of the beam solid angle and the effective aperture is the square of the wavelength. So if you know one of these in your wavelength, you know the other. Now, I would like to point out that an antenna and receiver is a remote sensing device. Here's where the temperature comes in. If you have a resistor at a temperature T, you will get a noise power in watts per hertz proportional to the absolute temperature in Kelvin degrees times this constant. That's Boltzmann's constant. If you replace this resistor by a dipole antenna that's at the focus of, say, a parabola with the antenna pattern out here, now you will measure a temperature here of this radiation resistance, T sub A, which is proportional to the power received in watts per hertz over Boltzmann's constant. And I wish to emphasize that this antenna temperature is not the temperature of the antenna structure. If it's a lossless antenna, the antenna temperature, the physical temperature, has nothing to do with it. This temperature is a measure of the temperature of the distant regions of space that are coupled back to the antenna by the radiation resistance. So a receiving system is really like a radiometer, where you've got a sensitive device, and through the antenna and field pattern, you are projecting your connections out and measuring the temperatures of distant regions in space. It's a radiometer, very definitely. Suppose, for example, that the antenna has an effective aperture of 10 square meters, receiving a 10 kilohertz bandwidth signal of 1 microvolt per meter. Now you'd say 1 microvolt per meter, that's fairly weak. I mean, that's nothing terribly strong. Well, then the received power figures out to about 3 times 10 to the minus 10th watts, rather low power. But when you figure out what the equivalent antenna temperature is, put that in here, and you put Boltzmann's constant, which is a very small number, and the bandwidth in here, you find that the equivalent antenna temperature is 2 billion Kelvin degrees. You're looking at a very hot object. And you probably don't realize it, but your television transmitting antennas, your antennas would look to a radiometer as something that's in the millions or billions of degrees. This is an equivalent black body temperature. It doesn't mean that your antenna is melting down or anything like that. Now, the minimum detectable temperature of a receiving system is equal to what's called the system temperature, divided by a statistical quantity involving the bandwidth and the integration time. For the OSU radio telescope, we have a system temperature of about 50 Kelvin, bandwidth of 100 megahertz, and time constant of about 4 seconds, so that our minimum detectable temperature is a few thousandths of a Kelvin degree. The signal to noise for this signal received with our telescope would be the ratio of this TA over this minimum, and it comes out to be 10 to the 12th, 1 trillion signal to noise ratio, or 120 dB. With big signals like that, people don't really worry very much about the system temperature and the minimum detectable signal. In fact, under many cases, it's not worth considering. But when you're working a system down to the limits, it certainly is. And for radio astronomy, for remote sensing, the temperature is very important. Suppose the radio telescope is looking out into space, and here is an emitting object at a temperature T sub s. If there was nothing intervening, the antenna temperature would be this. You would be measuring it. But suppose in between there is a cloud, a plasma, or something that is both an emitting and absorbing cloud, then the antenna temperature that you measure is given by this expression, where the source temperature is attenuated by the cloud, and there's an extra term due to the emission and absorption by the cloud. In remote sensing, you take a radio telescope up and put it on a satellite and turn it around and look back at the Earth. So here's the same telescope up on a satellite looking at the Earth. If you're looking directly at the Earth with nothing intervening, you would measure a temperature T sub E, that's the Earth temperature. If there's a big forest in between at a temperature T sub F, then the observed antenna temperature up there on the satellite would have this relation here. You have some loss by going through the forest, and you have a contribution of emission and absorption by the forest, exactly the same as in this situation above where you're looking in space. And it's with this kind of a setup that it is possible with these remote sensing satellites to survey large areas of the Earth, and from these various coefficients determine a great deal about the temperature of the Earth, reflection coefficient, the absorption of the forest or the cornfields or wheat fields or what have you. Do a tremendous amount of surveying on a large scale that has never been possible before, and this is a basic equation that is used in that work. Down here, let's place ourselves at the receiver terminals of a receiver connected by a transmission line of length L to an antenna. The transmission line has a physical temperature. This is what you'd measure putting a thermometer on it, and it has emission and absorption. It will have emission unless you cool it down to absolute zero. So there is a contribution from the transmission line, emission and absorption, and there is attenuation of the antenna temperature that you receive back there. And the interesting thing is that the equation and the relations for this system, transmission line, remote sensing, and a radio telescope are all mathematically identical. So we have two ways to go, and we often have to go both ways. One way with antenna systems is we study the three-dimensional field patterns, use Maxwell's equations, we have space vectors, function of angle, two angles, distance, and time. Or we can go the other route and deal only with simple scalars: radiation resistance, antenna temperature, beam area, directivity, gain, and effective aperture. That concludes phase 2 of my talk, and I would like now to go to the part I like best. That's the demonstration. Yes, but look at all this stuff here. Nobody has done anything about some of the very simple problems like that. When did this performance start? Does anybody have a time? I didn't even notice a lot. I left 5 after. We're running almost on schedule, maybe 5 minutes slow. I have here, oh, wait a minute, the lavalier. I'm 5 minutes behind. That's for them. Boy, they really check up on you here. They're timing you, everything. This is a 3-centimeter transmitter, 3 centimeter, power 10 milliwatts, modulated about 1 kilohertz. This is a receiver, very simple receiving device, feeding the output modulation into a loudspeaker, so that as I move this around and probe the field, you can tell by the intensity of the sound what's going on. You don't have to watch a meter up there jumping around and look at what I'm doing. You can just watch what I'm doing, and your ear will tell you what's what's happening. We're on the air. You can see the field coming out is quite well defined, just like the pattern I showed in the picture. Now, it's fairly narrow beam width. Now, if I move this one, you see I have to move it more to cut it out. That means this has a broader pattern. If we could draw balloons on here, this would be a sort of a Zeppelin coming out of here, and this would look like a hot air balloon over on this one. Wide pattern small aperture, this is about 1 square wavelength, that's maybe 10. So there's quite a difference in the patterns of these two. If I move this away, we observe that it goes down. That's the 1 over r effect for field, or 1 over r square effect for power. Now notice I turn this and it cuts out. That's polarization. This is vertically polarized. This is polarized that way. When polarizations agree, we get signal. When I cross-polarize them, it cuts out. My hand cuts off the signal. My hand also acts as a reflector. I'm not getting anything here, but I'm getting something back. If I put the receiving horn here, picking up some of this, and in a position to get something from here, listen. You can hear that I'm moving through a standing wave pattern. From each max to the next max, I have moved 1/2 wavelength, and if we had a meter stick up here, you'd see that was 15 millimeters, or 1.5 centimeters. Now, here's my hand. There are my fingers. Comes through my fingers, notice? Doesn't go through the palm, but it goes through the fingers. I turn the fingers vertically, and it cuts out. My fingers are a grid. They reject when the polarization is parallel to the fingers, and the signal goes through when it's perpendicular. So my fingers can act as a grid. Let me repeat that experiment with I did with my hand and getting the standing waves using this thing here. It has a sheet of aluminum on here, an aluminum sheet. I can demonstrate that here. You see there's specular reflection. When I get it turned just right, I get a signal out and back, angle of reflection equal to the angle of incidence, all that sort of thing, and it works very well there, but I don't get much back when it's turned at other angles. Now, this works better than my hand, and besides, my hand was getting hot. So, you get the standing wave effect very, very nicely. Now this, you notice, reflects very strong. But if I just turn it over, I don't get anything. Nothing. Nothing at all. Wouldn't you like to have some of that to put on your car as a fuzzbuster? Well, it's cheap. You just get what is called space cloth or space paper. I have some paper here that has a resistance per square. Any square you cut out measured from two opposite sides has 377 ohms. That's the impedance of space. And I backed it up with that aluminum sheet that was reflecting off the other side. So this is a dual purpose device here. And this absorbing material with a quarter wave behind a reflecting sheet completely absorbs the incident signal. It's a beautiful demonstration of the fact that physically space has an impedance. 377 ohms approximately, and coincidentally equal to approximately 2 pi times 60, but it has nothing to do with the power frequency. It's coincidental. Now, here is the signal coming through, good and strong. I have here a little paddle. I put it in, nothing happens. Doesn't do anything. But I turn it over, cuts it off completely. Flip it over, it goes through, turn it over, nothing. I must have some kind of unidirectional device in there. No, not Zener diodes, but you know, something that works one way, clamps them the other way, so that nothing gets through. Well, as a matter of fact, I don't. I have something like my fingers. I have a grid of wires in here. And you see, the grid is in at this angle, and when I hold the paddle like that, the grid's horizontal. When I flip like that, the grid goes vertical. So the trick is you put this in at 45, and you can go from complete reflection to complete transmission. Now, let's extend the experiment. I cross-polarize the receiving antenna. Nothing is coming through, and I'll now put in this grid of wires at a 45-degree angle. And you see, signal comes through because the grid is this way, and the field was polarized like that, but the only field that can get through is at this angle, so it lets the field through that way, and that has a component in this direction of the receiving horn. If I put a couple of these, or a series of them, I could rotate the field as much as I wanted to, so the grid can serve a number of purposes. Now, you're all members of the IEEE. How many of you are? Let's see. I'd like to report to New York that it's 100%. Oh, golly. Well, Spectrum is their magazine, in case you didn't know that. A very excellent publication. The IEEE is the largest professional organization in the world, and they do a tremendous job. The Spectrum is very good, very clear, transparent. Comes right through. By contrast, here is the Ohio State University Graduate School Bulletin. You know, don't you? Tough school. Well, it's maybe hard going, but there's really must be more to it than that. And if I look through here carefully, there we find it, an aluminum sheet. That did it. Now, here's this polarization again. You notice? Cuts out. Now, if I put in this thing here, it looks like a 100-millimeter cigarette, but this one's better for you than the real kind. And see what happens. Keeps right on going. I've overcome the polarization problem by putting in this little paper cylinder a helical antenna for 3 centimeters. And it makes this a circularly polarized receiving antenna, so that this will receive any linear polarization equally well. Now, engineers are always interested in gain. How are we going to get another 10th dB gain? Let's get more gain, put bigger antennas up, crank up the transmitter, all this stuff. And so you want to lay down a big field out there, or if you have a fixed field, What do you do to increase it? Well, you get more aperture. Here's a that should be a 10 dB increase because this is up to an aperture 10 times as big as this one. But it was a little mismatch here. This isn't a perfect way to couple these two, but for a simple demonstration, it's all right. Now, there are other ways of getting improvement. You've heard of polyrod antennas. Let's try one of those. Here's a plastic rod. This cork is just simply so it'll hold it in the horn. You notice how narrow the beam width is now. There are some fairly big side lobes. Now this has about the same improvement as this horn does. This horn, we can see that we have an increase in effective aperture over this little one. But here we've actually got a physical aperture that's very small. It's just the cross-section of that rod. Yet the effective collecting aperture, the A sub E for this, would be something about this big probably, which means that this rod acts like a lens. The wave coming in gets pulled down, sucked in. This is an elongated lens. Polyrod antennas are very effective. And did you know that the retina of the human eye has 100 million polyrod antennas in it, connected by several million axon nerve transmission lines to the brain where the signals are processed and the image is formed. 100 million polyrod antennas in the retina of an eye, and these are operating in the eye at light wavelengths, which means that they're about 1 million times smaller. The principle is identical, absolutely identical to a polyrod antenna, except that they are astonishingly small, and 100 million can be packed into the retina of a single eye. Well, the polyrod antenna, I said, was like a lens. Let's try an actual lens. Here's one made out of paraffin. I'm having a little trouble focusing it. But you notice that I was turning it a lot this way. That's an interesting thing about lens antennas. The alignment is not critical at all. You can be sloppy as hell how you set these lenses up, and they work fine. Well, to get waves from one place to another, we use transmission lines, waveguides for these frequencies, but let me demonstrate this antenna here first. The ultimate in size is often a parabola, And I have here a navigational radar used on aircraft for 3 centimeters, and we'll take it out here in the boondocks from this radio transmitter, see how we can pick it up. A large increase in signal, and you notice that the beam width is quite narrow. I did not have to move that very much. Now there's a very simple relation that the beam width of these antennas is often something like 60 or 65 divided by the aperture distance in wavelengths. This measures 48 centimeters divided by 3, that gives you 16, and suppose the magic number is 64. That means divide 16 into 64, we would have 4 degrees calculated as the half-power beam width. And I was moving it a little more than that because I was going more like from the twice the half-power beam width. I was going between the nulls on either side. Half that is about 4 degrees. Theory and experiment agree quite well. And the beam is wider this other way. This is a fan beam, beaver tail, whatever you call it. Oh, I forgot something. Going along here and I just slipped over it. Here's this polyrod antenna, and it's linearly polarized. But let me slip a little helix over this polyrod and look at what happens. Becomes circularly polarized. Just put a few turns of wire on there and we've got a circularly polarized polyrod antenna. Waveguides are used to convey these short waves everywhere. Here's a piece of pipe. We don't get much here, but we drop a pipe down into the path. Okay, let's take a smaller pipe, in diameter, I mean, see if it works. Yep, comes through. Let's go for a still smaller diameter. A little bit smaller. Nothing. The pipe is a little too small to let this wavelength go through. It's not much. It's only a millimeter or so too small in diameter, so that this pipe cuts off the wave completely, where our wave is beyond cutoff for this. But how about putting a plastic rod down through the inside of that pipe? See what happens then. Comes right through. We have loaded the interior with dielectric. We've increased the cutoff wavelength so the wave goes through. So if you have waveguide and you're not getting something through, just pour something in and increase the effective diameter. Now, here is a corner reflector. This is 3 reflecting planes mutually perpendicular forming a corner, and these have an interesting property. They're a retro reflector. A wave coming in from anywhere in this quadrant, octant rather, hitting one of these will bounce off this one and the other one, and it'll come back directly to the source, so that it is a retroreflector. And it's very hard for me to do this because I can't put the receiving antenna inside the transmitting one. But there are some maxes and mins on it, but you see it's much more effective that way than in this direction. In practice, these are usually made up, well, for radar purposes. You take a conducting plane this way, one this way, and a third plane so that the three are mutually perpendicular. And in order to reduce wind resistance, you may make this out of screen where the whole mesh is not too small compared to the wavelength. And you put this on your little sailboat, and it makes it give a radar return as big as the Queen Elizabeth II, so that you won't get run down in the fog in the harbor. And you'll notice that these little boats running around often have these corner reflectors on them for increasing their radar return. I have here some aluminum sheet, and I'd like to demonstrate a very practical situation. I'm going to make a ground plane, convert this tabletop to a fairly good ground plane. It's not quite as flat as I might like to have it, but now if I go out here at some distance from the transmitter, and raise and lower the height of the receiving antenna. This is a very typical situation. You have a transmitter, broadcasting transmitter on a tower. You're out here at some distance from it. You're trying to get a good signal at your receiving location, and you find that at some heights you don't get much at all. So you say, well, we've got to build a taller tower. Yeah, that would help, but you could get the same increase by going lower. Instead of adding on, you could take a saw and cut the tower down. Keep that in mind. This is one of the problems. You have spots where the direct wave and the one that's bouncing off the ground reinforce, that's fine. But where the two are in opposite phase, they cancel and you get no signal. And so you have to go up or down. Or you can go to circular polarization. I will make the transmitter now circularly polarized to a degree by putting on this helix here. And I'll put the helix in this receiving antenna. And the matching here is not too good, but I think it will illustrate what happens. Cuts off here. But the signal is essentially constant as you go up and down. That's the beautiful thing about circular polarization, as long as the receiving antenna is of the same hand as the transmitting. This is right-handed, this is right-handed, and this sees only the direct signal. The one that comes off the ground gets reversed and comes up left-handed, and this is blind to it. So circular polarization is a way around the problem of ground reflection, or the first reflection off of anything, sides of buildings or what have you. That concludes the demonstration almost. When Heinrich Hertz built his spark system, he didn't bother to get a license. If one had been issued, I think that this that these call letters here would have been appropriate. DJ for Germany, 4 for Karlsruhe, and HZ for Hertz. DJ4HZ. Now, it might be difficult to get a license for a spark transmitter now. But curiously, our high voltage lab at Ohio State University produces sparks that are 1 million, maybe 1 billion times more powerful, but it hasn't any license. Neither do the 100 million gasoline engine ignitions, nor the ignition systems on oil furnaces or spark cauterizers, coagulators, ozone producers, spark induction heaters, or diathermy machines. So, if you will regard this equipment as an ignition system, I will recreate for you a moment 95 years ago when radio was born in the Karlsruhe laboratory of Herr Dr. Professor Heinrich Hertz. If you would cut the auditorium lights, put on the spot, please. Guten Abend. Danke. Augenblick bitte. Vielleicht endlich mein Apparat fertig ist. Ganz gut. Es geht. Ausgezeichnet. Wunderbar. Lights. We hear about antique radios, old Marconi sets, Atwater Kents, but this one is the most antique radio of all. Thank you.